Hi guys, thank you for coming to this talk. My name is Jeff Tratner. I work at Counsel, which is a company that does DNA testing. So like if you're thinking of having a kid or something like that, you send us your DNA and we sequence it and then tell you about your results. And we use Pandas there for some of our data munging tasks. But the reason that I am talking about this in particular is because for a while I was a very active contributor to Pandas overall. So yeah, and actually I'm really excited to be here in particular because PyData NYC in 2013 was the place where I got my first job in tech. So it's like really exciting to be able to be on the other side and giving some cool talks. So just let's, hold on. So to quickly talk about Pandas, so it's like a really large project. So you can see that there's like 12,000 commits, there's about like 200,000 lines of code, 400 contributors, which is awesome because many of them are people who like put up one PR and something small and like contribute in. And it's really great. I think it's one of the, just a really amazing community. It's been around for about 6 years and you can see like the development activity has shifted a lot. Wes McKinney, the person who started it, was really active, and now Jeff Reback has been doing an awesome job. I am sort of number 9 on this list. And I've kind of tailed off in my commits, but I still have some memory of Pandas overall. And so with this big history, with this huge code base, with all this stuff, it can be like a little intimidating to figure out what's going on behind the scenes with Pandas. So what I'm gonna try to do here overall is give you like a little bit of orientation into some of the really key concepts in Pandas so that if you wanna dive deeper, you kind of have this like high level idea of what you wanna be doing. So kind of like we're gonna give you like guideposts and stuff like that. So I'm gonna just do a little more introduction, then I'm gonna give kind of a background into the many Python data analysis libraries that Pandas kind of works on top of, because there's just a bunch of them, and also talk about like why wrangling data in Python, you can't just do it at like a pure Python level, like why we have these specialized libraries to do it. And then I'm going to talk about some of the really fundamental Pandas concepts from the implementation side. So indexing, grouping and storing data, and finally in terms of factorizing overall, which is like sort of used a lot through the Pandas code base. So these obviously aren't all the things that Pandas does, but they're sort of important areas, and I think getting a little insight into them will give you a different sense of the library and also help understand maybe why certain things are fast or slow or considerations that you want to have. So let's start out. So again, lots of lines of code. It depends on many other libraries, and we're going to talk about sort of the key concepts. So I just want to like take a moment. I know I've like said this twice, but the Pandas community is amazing. It's like one of the most welcoming open source communities I've been a part of. So if you feel at all like, hey, something should be better with Pandas, or I really wish Pandas did this, I really encourage you to go out and like try to contribute to it, because it can be a really great learning experience and it's really fun, and it's like a great feeling when your code ends up somewhere. So go contribute. So I'm hoping that most of you guys have a sense of Pandas. Like how many people have at least heard of Pandas before this? Okay. Awesome. So I would hope so. But so overall, I think that the key thing that Pandas does is it provides a really flexible API over data, and in particular labeled data. So if you're thinking about NumPy, it might be more about like integer indexing, stuff like that, whereas Pandas is more concerned with like, I have this metadata and I want to be able to use that to group, select, combine, filter, and transform my data. And then also it has a really big component that I'm not really going to talk about much here of getting data in and out. You can go from a whole bunch of different formats to another set of formats very easily and transparently, so it makes it really easy to get data in there. And it also works well with other Python data analysis libraries. But the context for this is making it easy to manipulate data in a fast and performant way. So let's talk quickly about like what is kind of going on behind the scenes in Python that's kind of contributing to why Python's slow. So Python is super duper flexible, right? Like you can set a property on an object, you can override addition, multiplication, division, literally everything. And you can do that and it's great, but it also means that when you see something kind of simple like this particular thing, it looks really simple, right? You're like iterating over an array on every element, you're maybe taking the log of it, you're doing some multiplication. Like this seems like something that shouldn't be that big of a deal. But the thing is that because Python is so dynamic and flexible, this translates into these kind of operations behind the scenes. So the way you should interpret this is that this is kind of the way that Python compiles it to a list of commands, right? So you see the loop starting, there's some loading of names, which basically means like, okay, I gotta go look in the global namespace and up and up and up until it finds the definition of it or throws a name error. But one thing you can look at in particular is look at how, because you're using I 2 times in this loop, there's no like caching. There's no, hey, I totally know that this I is going to be used twice. Instead, it's just like, I'm going to have to look it up every time. And similarly, with the log function, it has to be looked up every time. And that's partially because you can write a function that literally changes the global namespace, so the next time you call that function, it's different. Or the same thing with properties on objects. So all of this sort of dynamicity causes a lot of overhead. A lookup in a dictionary is fundamentally expensive, but when we're talking about expensive here, I just want to be really clear that we're talking about that in the concept of like arrays that have hundreds of thousands of elements or millions of elements. So when you're thinking about, hey, I want to add one to every one of those things, if you have to do this lookup every single time when you're doing it 100,000 times or 1,000,000 times, that's when that overhead of looking up a function, of looking up a value starts to get really high. So one way that you can avoid this overhead is with the Python C API. So it's kind of like lets you choose when you want to bubble up to the Python level. And the Numba talk in particular talked about some ways to avoid the GIL. And so that lets you write code at the C level and get some like nice optimizations, a lot more control over memory management and stuff like that. Another component, so it's kind of just like there is a way to interact with code at the C level, and the Python C API is non-trivial, so I'm just going to kind of hand wave there. But the other part of this that happens too is that individual Python objects have a lot of memory overhead. So if you think about like a C integer, an array in C is literally just a set of boxes, like at some level, that are sized exactly for the data that's inside of it. But when you're thinking about it at the Python level, there's a lot of overhead that goes into here. So this Py object head that you see here on this slide, that involves a lot of the bookkeeping that Python does, so you don't have to manage memory. So a reference count, which gets incremented every time you say A equals B, or stuff like that. The type of the variable, which impacts like how lookups happen, and then finally the value itself, or maybe a pointer to the value. So that means, again, if we're thinking about this on the level of hundreds of thousands of Python objects, every one of them has to have this overhead. And these images are from Jake Vanderplas's awesome Why Python is Slow, which is a great blog post that kind of goes more in depth into it. So I'm just kind of stealing them to make for a better summary. So this particular issue comes up even more when you're thinking about a Python list, where every single element, where the list itself is an object, so it has that overhead, and then every element in the list is a pointer to another Python object. And so the problem that happens there is that you have this array that when you go over it, every time you're going to have to do a lookup, which means that, you know, if you kind of see how crazy these lines cross and stuff like that, that means that maybe you're going to break the CPU cache, or you're going to need to be loading in different ways. And no matter what, that all adds additional overhead. So that's like kind of another component of the things that we want to avoid. And one of the ways that we can make this better is by using a NumPy array. So a NumPy array is essentially like around, and again, this is like super high level, but is around, basically lets you have that value of a C integer where like boxes are exactly sized to every component, but still be able to interact with it in Python and C and Fortran. And so now that you have like kind of the data locality that you want, so you're not sort of crossing over between CPU and you know, can do better cache performance and things like that. So NumPy overall, it's enabling like fast vectorized operations on arrays. So it's a pointer to memory in Fortran. There's a lot of scientific code that was written a long time ago in Fortran, like Blaz and Lepak, and I think Atlas, that are really sturdy. It's written very well, it's well optimized, and so NumPy lets you pass in these arrays to those kind of functions to get those sort of performance optimizations while still being able to write Python code. And so this idea of vectorization, to be clear, is just like you do some operation on every element in an array so that you can stay under the Python level and not incur sort of the overhead of having to look up a particular function or a value or something like that. Okay, so, but the issue with NumPy like Travis said in his talk on Numba, is that you have to write functions for it in C. And that's kind of a bummer because then you have to handle memory management and you have to handle, all the different ways that things can go wrong and cross-system compatibility. So the next kind of level that we're adding here, in addition to NumPy, is Cython. So Cython is this subset, or sort of like a version of Python that's typed. And because it's typed, it lets you be able to express really elegantly sort of transformations with NumPy, but without having to necessarily write all the bookkeeping code for it. So we have this particular lookup function like this. You can see that it has the sort of CDEF part is saying, here's the types of the things that I'm going to be using, and you're very explicit about it. And then this for loop and things like that get translated. And you can even inline functions, you can call C functions, and then if you need to go up to Python level for something, then you can do that. And so the output of Cython is super complicated. It ends up compiling to this C code where the comments are like each individual line where you're seeing what's going on. And I just want to if you take this part right here, you see how many lines there are here? This is kind of like a representation in C code of how much bookkeeping there has to have around Python stuff. Now this is more kind of the bookkeeping about making sure that you've accessed an array appropriately, like you haven't had overflow, you haven't done various other things like that. But all of that bookkeeping is what's happening under the scenes every time you do a list subset or every time you're talking about reference counts or things like that. But then if we look at this line here, this kget in 32 is actually this library klib that we'll talk a little bit more about later. That's a C function, and because you're at C level, you're using a value that Cython knows is able to be passed that function and everything like that, you can actually call it directly in C, which means that when GCC compiles this, or whatever compiler you're using compiles it, you can get the kind of compiler optimizations that you want, and you also get to have very better memory management and stuff like that. So that's kind of Cython. So then we have Cython, we have NumPy, and then another level that comes on top of that, again for more optimization, is I actually don't know how to pronounce this, but I think it's NumExpr or NumExpression. And basically what that does is it lets you say, okay, I want to do this complicated set of operations on a NumPy array. So generally, if you take this formula right here, 2 times A plus 3 times B, what happens if you do that at Python level is 2 times A happens, and then that forms an intermediate array. And then probably 3 times B happens next, so that's an intermediate array. And then you add them together, and that forms yet another intermediate array. So what NumExpression does, and this gets used in Pandas to optimize some of the slow parts, is basically say, okay, I totally know that on this for loop, I'm going to be doing all of these operations on every element. So instead of going up and down and doing copies, I'm just going to stay at this lower level and work on buckets of the array doing all the operations at once, which gives you the ability to not have as many temporary copies. So in terms of bytecode wise, it ends up looking sort of more like this, which is where each component is some chunk of it that it works on and does these operations without having intermediate copies. So this is sort of another level of sort of the many layers of stuff that Pandas is on top of. So if we just stopped here, we would have a really great thing. We have NumPy that has good data locality and fast performant operations like sine, cosine, addition, things like that. We have Cython, which lets us write universal functions for NumPy, and we have NumExpression and many other libraries like it. There's another one called Bottleneck that lets you compile NumPy, basically compile and JIT your operations. You could even use Numba and stuff like that. So the question here is why would you ever use Pandas on top of that? And I think probably you guys have some sense of why that would be, but the basic reason is that all of those things are great when you want to optimize code in particular, but the sweet spot would be being able to have heterogeneous data types. So not just saying ahead of time, I have an ND array and it's int32 and it has 20 elements, but being able to sort of write code that's very generic and be able to have easy missing data handling and basically be able to deal with labeled data in a way where you don't have to specialize for every single kind of thing that you're doing. So in particular here, what we're talking about is that you can load something from a CSV, have no idea what the data format is inside of it, but still take advantage of kind of the optimized algorithms and routines that Pandas and NumPy and NumExpression and all of those different levels provide. So that's kind of the overall reason that Pandas exists and is useful, is to be flexible in that way. So, and I think the point that is most relevant for pandas is that it provides a better sense of labeled data, because essentially, like, if you're thinking about a NumPy array thinks that, okay, integer index 0, integer index 1, integer index is 2, that's what's important about this. Whereas pandas, we're talking about the index as this element that's really important. So that's so that leads into this next section. When we're talking about indexing, that's a really important pandas operation that underlies a lot of the stuff that's going on. It's the way that you transform something where there's a set of labels that you care about from a business perspective or from a user perspective to the set of like elements from this array that NumPy needs to work on. So we have this core pandas structure that's a data frame, just to like make sure everybody's on the same page. So indexes are kind of the columns and the rows. And I'm just gonna, as an aside here, Pandas supports like multi-dimensional data sets, right? You could have like 3 dimensions, 4 dimensions, but honestly, like, it all is kind of the same idea. So I'm just gonna stick with the data frame when we're talking about this stuff, because it's just a lot easier to think about. So you have indexes, you have like the internal data that's stored in those indexes and that the columns and rows represent, and then individual columns we kind of call series. So it's like a one-dimensional data frame. So when we're talking about kind of the basics of indexing, the big issue is that indexes are a big mapping. So let's say that like A, B, C, D are some list of products or A/B tests or something like that. Basically, the main thing that the index does is when you say, I want C, it says internally, okay, that's index 2. That's like the main role that an index does, but that's sort of complicated once you get to more things like alignment and merging and joining. But that's like kind of the key thing to keep in mind. It's like a big dict mapping labels to integer indexes. So you want to read this as like row C maps location 2. It's sort of the metadata on a data frame that we care about. And then obviously, like, you can convert any series into an index. So like kind of that's just the overall thing. And then a really key point is that indexes are immutable. And that kind of matters at some level because it means that you can share indexes between components and you can do a lot of kind of expensive work behind the scenes to construct an index. So, okay, again, task 1, lookups. You have some label, you look it up, you end up with values on top of it. So this is like, you're saying lock C, which means you're gonna get that row. If I said quantity, I'd get like 523, 200, 148 with that index. Now, the next task that indexes do that I think you kind of like intuitively understand, but maybe you have, I definitely didn't necessarily think about what the heck was going on behind the scenes, is taking 2 different data frames that have similar metadata. In other words, we're saying that this first data frame and this second data frame are still referencing the same ideas. They're referencing the same set of products, and the columns that are there mean the same kind of values, but we want to be able to combine them. So for NumPy's perspective, the only thing that matters in general is ordering. Or maybe you pass like an array of indices to NumPy as well. But it's not necessarily as transparent as Pandas is, where you just say A plus B. So what the index is going to do here with these 2 data frames is make them compatible. So let's say we're thinking about adding these 2 together. So take a second and think in your head, like, what do you think the output should be? Like, if you're thinking about, if you use pandas already, you know, but like, what does it mean that, for example, points is missing from the second one? How do you end up with a data frame combining the 2 of them? Or the fact that like row F is missing from the second part, or they're in a different order. So, if you know pandas, what ends up happening is that you have NaN, which means like missing values in the third column. There's no points in them, so it doesn't mean anything to combine them. There's no row F, so in the output that also doesn't mean anything. And then you also notice that it's like reordered. So let's think about how that alignment happens. Because basically what's going on behind the scenes, the first step is to say, okay, I need to get this into a format so I can pass 2 NumPy arrays to NumPy to handle like the optimized part. So what needs to happen here is we just need to use the indexes to be able to get them in the same format, so then we can combine the columns. So basically the sort of get indexer method, what it's really responsible for is the same goal of the index that we talked about before, taking a label and ending up with a set of integer locations. But in this case, it's going to be the set of integer locations that you can use with that second data frame that will give you the same ordering, that'll give you like the right ordering to be able to combine with that. So basically, if you're looking at the first item, it's saying, okay, A, where is that on the second index? That's at index 1. B is at index 3. C is at index 2, and so forth. And then the problem is when you hit like a missing value, what that ends up getting represented as is -1. That's just sort of like a convention. So then when you end up with the aligned data frame, and I kind of, when I made this up, I just tried to keep the quantity the same as the index just so you can see it. You end up with it basically reordered so that it matches the order of the other data frame. So that's kind of like what indexing is doing. And I know, again, this is some stuff where it's like sort of straightforward, but also I think when you think about kind of how these pieces are split apart, it makes it easier to understand why there's so much crazy code around indexing. Because if the indexes can manage this transformation well, then other parts of Pandas like don't have to be concerned with that. Okay. So the next thing that's going on here is you think about like, this is like a 5-element thing, right? And you have to do like 5 lookups. But again, when we're talking about this, we're talking about this on the scale of like really huge indexes. So maybe 10,000 items or 5,000 items or larger than that. So the issue becomes, if it actually were a dict behind the scenes, you'd still have that same issue of, oh my gosh, here's Python functions, there's objects, I'm going up and down in level. So the question is like, how do you handle that? So if you want to do tons of lookups really fast, the Python dict implementation is actually pretty fast. So that was kind of what Wes McKinney used to start with. But now what Pandas uses behind the scenes is this C library called klib. I don't have like a great picture of it, but basically what you should imagine that klib does is it has an internal dict representation that's very fast and that you can do all at C level. And the other thing that it does is lets you say, here's the type that I have. I will make a really specific typed dict that is expected to work exactly like that type. So there's an int32 dict and a float dict and that kind of stuff. And what that lets you do behind the scenes is it lets the compiler do all the kind of optimizations again. So this lets, basically what happens is that, it's specialized by type. And what this lets you do is like when we do alignment behind the scenes, it's literally just iterating over every index in one of the indexes and grabbing the value from the mapping in the other index. And that's fast enough to be able to do it on like even a really big index. And so if you remember before from that Python slide, we had that kh get int32. That's kind of what ends up being littered through the code are calls to the klib libraries or the klib functions that pull out from a mapping. So also, we were talking before, or I mentioned before that indexes are immutable overall. And that's why this is important, because building up this mapping is expensive. It's expensive to iterate through every item and factorize it and put in a value. So an index under the hood shares the individual mapping each time. So even though you have a different Python object, so you can manipulate the name and stuff like that, the kind of behind the scenes part is shared between them. Okay. So that's kind of like the basics of indexing. And like, part of the problem here is that I would love to go way more in depth, but I kind of want you guys to have a sense of like, here are the components so that when you go and look at this, if you wanted to go look at this indexing code and you see like, hey, there are like 20 functions that all have underlines in their names and they're doing crazy stuff, you can keep in your head like, yeah, okay, all I'm trying to get to is integer indexes and be able to kind of think about it through there. So let's imagine that we have some data in a CSV. So there's something like this, like a timestamp, UID, product, whatever, just some set of data that we want to load in. So if we loaded this with like the CSV module in Python, right, you'd end up with just a bunch of strings, and then it would be hard to convert. You have to write some specialized functions, things like that. So Pandas has essentially like relatively optimized code specifically for parsing CSVs, and then more broadly for parsing data overall. So the C engine for CSVs in general is basically just a reader that lets you specify a subset of columns so that, I guess if you have like a really huge CSV, you can read like 3 columns in or something like that. But kind of the magic that's going on behind the scenes that can actually be sort of problematic when you want to have really performant code is that the readers in Pandas will try to convert types. So if we go back to this like thing here, basically what's going to happen is that like for every row, it's going to try to convert this to an int. Once it finds out that doesn't work, stops. Try to convert it to a float. When it finds out that doesn't work, stops. Try to convert it to a bool, etc. The same thing with like NA values. And similarly, it tries to do date parsing to be able to say, okay, I see that this like is, looks like a date that I kind of know about. Let me try and convert it. So I think for really big data frames, it's only going to take like, maybe the first whatever number of thousand rows and go over that. And usually, I mean, if you think about it, you can generally get to that pretty quickly. But one issue that comes into play is that Pandas can only give you a value if it's compatible with like every element. So for example, if you have a column and every single entry is, you know, an integer, except for one row that's a string. Well, when you're converting it back in, it's going to all have to be string, so it all fits there. So that's kind of like what's going on behind the scenes when you're reading in data. And then, so like Excel uses the same thing. So, okay, so now we have this data that's converted into, you know, the right type. And at this point, you could kind of think of it as being like a dict mapping columns to ND arrays. Like, okay, I figured out that the timestamp column was a date. So now I have like, you know, the label, and then I have like an array of date times. Well, date times 64 NS, which is the NumPy type. But what happens behind the hood is actually sort of similar to what, to the talk earlier today. The data gets split up into blocks by type. So what's going to happen is like all of the columns that have string values get grouped together, and all of the columns that have integer values get grouped together, and so on and so forth. And the reason why you'd want to do this is basically that it's kind of that same, well, there's a couple reasons, but one of the biggest reasons is that like NumPy operations are again set up to work on like multi-dimensional arrays, big groupings. So if you're thinking about, hey, I want to do some operation across like 3 columns, storing it in this way lets you do that operation without a copy. Because again, one of the big things about these blocks and about NumPy arrays is that they have to be a fixed size. So NumPy needs to know ahead of time what the size is, which means that if you want to use like 3 columns together, to be able to pass that into a function in NumPy, you're going to have to combine that all behind the scenes. So instead, what happens is that they sort in blocks, and so there's a BlockManager that handles converting the request, like for an index, like I want values A, B, C, whatever, to kind of more internal sort of stuff. So so the BlockManager is more focused on like getting the data and also like directing changes to the right row. Whereas the blocks are kind of specialized by each type. And if you look at these blocks here, right, like these ones don't have indexes that represent the labels that you care about. They're all integer indexes. Whoops. So what that means is that you're going to end up being able to write operations on blocks that only care about getting those integer indexes and stuff like that. So again, lets you kind of have this like separation of concerns. Granted, if you go look at the code, that separation is not perfect, but it certainly is like kind of, you know, a way of translating it. So this is like one of those points where I think understanding that behind the scenes there are fixed size blocks in pandas lets you actually understand why some of the operations can seem so weird. So one thing in particular that happens with pandas is copying happens a lot, right? So basically like, if you end up copying data, that can be really problematic if like your data takes up half your memory. So if you're thinking about like what stuff you can do to just keep a slice as opposed to a copy, thinking about blocks is the big thing. So when you're slicing within a D type, you can keep one, so by D type I just mean like within one set of blocks, you can keep that kind of slice, because in NumPy, if you specify like a slice of values, then it says, okay, all I need to do now is take this pointer that was pointing at the head of the list and just say now it only has 4 elements as opposed to like 10 or something. So you end up with a view. And that's like a whole other complicated thing that I don't really have time to go into, but you can sort of just, so you end up with like a slice. So when you're slicing within a single D type, you can just like say, okay, I want like this group of things. It gives you back a view. It's great. But the problem becomes that when you have like a slice that crosses D types, or a slice that does fancy indexing where you can no longer like have that like direct mapping, you end up needing to copy. And the cross D type stuff is, I think, more just because like the bookkeeping is sort of more complicated. But so overall, it's like that is maybe, if there's like one thing you can take away from this talk, it's like slicing in a single D type versus across multiple is different. And then also, if you guys have been using an older version of Pandas and then recently upgraded to like 0.15 or 0.16, you probably have hit setting with copy as like a really crummy thing that crops up and is confusing and stuff like that. And this is sort of like one way to understand what the heck that setting with copy errors means. So what that's saying is that underneath the hood, sometimes when you slice, you can be manipulating the same block. But if you slice in a way where you're causing a copy to happen, then all of the changes that you're making to that other data frame aren't going to be reflected in the BlockManager, because it is a different BlockManager with a different set of data and a different set of copies. So the goal here, basically with that error, is just to make you aware, so that if by accident your code that references column A and column C suddenly changes to be like, oh, those are now 2 different D types, you don't have this like magical confusing error that's going on behind the scenes. So the other thing that Pandas developers talk about a lot is that appends are expensive. That in other words, like you think with the Python list, you're like, oh yeah, I want to add an element. I will just append to it. And you don't really think about like pre-allocating. So blocks again, and also like sort of the stuff with NumPy are the reason why appending ends up being expensive. In other words, like if you append an element, suddenly you've taken your fixed size block that used to be like 10 by 10, and now you want to make it 11 by 10. And in NumPy, that's something that has to result in a copy. You have to copy it from one place to another. And you know, basically, if you're thinking about this, like that's, I mean, it should be pretty straightforward. It's just like, yep, that's like a property of NumPy. But the other thing is that if you wanted to say like allocate additional data, you hit this issue that because copying is happening behind the scenes in Pandas, allocating bigger blocks just by default would also be problematic, would also start eating up more of your memory and have like different set of performance considerations. So like ways to deal with it, basically you can yourself pre-allocate memory, so like zero out spaces to start with, or you can pull everything out into Python, or you can also just build up a bunch of individual frames and then concatenate them so you only suffer a copy once. Okay, so that was like one key area of Pandas, storing data, getting data. We've talked about indexing too, which is sort of like the other really important Pandas operation in alignment. So for this last part, I just want to talk about like, so group by is a really cool key Pandas thing. It's really elegant, it's flexible, it's usually pretty performant. So I'm just going to talk about kind of the algorithm that underlies that, because I think it's kind of cool. And Wes McKinney has a talk from PyData NYC in 2012 that goes a little more in depth. So I'm just going to kind of cover the highlights of it, because I really want to give you guys time to ask me questions or whatever if anything's confusing. So factorizing basically means mapping repeated keys to integers. So it sort of looks like this. You're going to iterate over an array, and every time you see a new element, you assign it like 1, then 2, then 3, then 4, then 5. So you end up with a mapping of a dictionary of essentially like this particular factor like means this value or something like that. So you can like map the way. I think I flipped one part of this, and it should be factors max factor equals element, but no, that's right. And then you end up with a set of indexes that map those things back. So you have, essentially you end up with like a couple dicks behind the scenes. So you use this in a bunch of places. Again, group by uses this, in other words, to have like a set, and I'll kind of show a little more like why this matters. Uses this to basically say, okay, I want to do a grouping operation, but instead of having to write a separate algorithm for floats and for strings or for multiple columns or stuff like that, I only need to write one algorithm that assumes that I have a list of integers that say how things are grouped, plus the data that I care about grouping. So that's kind of like what's going on here. Categoricals are another area where this kind of factorizing comes into play, because you basically, instead of having like a string column with like 100,000 entries, each of them repeated, you can sort it as an integer column, which is like a lot smaller and also has some performance benefits that, again, I don't necessarily have time to go into. And this is another area where you just use klib to take advantage of faster performance and the ability to stay down to the sea level. So let's think about like why this is useful. So the one really cool thing to think about with this is just counting sort. So essentially what this is a sort that lets you avoid doing n log n comparisons. Because basically if you know that you have like low cardinality in the particular like array that you're using, if you know that you have maybe 100,000 items and only 10,000 of them are unique, or probably like a little smaller than that, you can actually change how you're doing the comparisons so that you don't have to compare each element. So in other words, if you go through and you hash, which again is essentially like O of n, hash each element to an integer, then all you need to do is collect the integers, sort them, and count how many you have, and then you can just pre-allocate the buckets and be able to put things in those places. So that lets you be able to, for example, sort things by a combination of columns, and kind of, it just ends up being like a faster sort overall. And I guess I bring this up because the same sorts of optimizations apply for sorting as you can get with like summing or finding the minimum in a particular bucket. The same idea where when you can scan and know that you have already the cardinality put through, you can figure out what those values are or do a grouping operation or subsetting relatively quickly. So this expands to be a little more complicated when you're thinking about like 2 columns. So like with 1 column, pretty simple, right? It's like, okay, I have like 1, 2, 3, 4, that's awesome. But if you have multiple columns, like how do you combine them? How do you take 3 columns together and end up with like a unique value for each one? So essentially, you start out and you factorize each one individually. So now you have 3 columns, each of which have like independent factors in them. And then when you combine them, you essentially like multiply the key space together. So it's like maybe you have the first column, and then the second column is like, if the first column has like 100 values, and the second column you multiply 100, third column you do again, and then you sum them together, which ends up with like a unique key for every element. But there's kind of a problem there, right? If you're getting the cross product of all those columns, you have this huge space. And what we were saying before is that counting sort and all of these things where you're like going through is effective because you know that you have like a really limited set of values, because you can just say, okay, now I want like value 1, value 2, value 3. So to get back to that, you actually just do it again, because you know that you have like a really small set of values, so you just factorize that cross product. And now magically you're back to where you wanted to be in the beginning. You know that you have some low number of unique values in that grouping, and you're able to take advantage of all like the kind of fancy algorithms for that. So yeah, and again, this means that all the algorithms that you write, when you want to write like a algorithm for aggregating stuff, it means that you don't have to write like 3 different algorithms for all the different ways that you could have keys, and instead you just have to write like one algorithm that says one algorithm for every aggregation type that says I have like this set of integer labels, and it goes out. Okay, so that's kind of like covering the set of things that I wanted to talk about, while also leaving you time to ask me some questions and things like that. So let's just like recap. So the key to doing many small operations in Python, which is essentially the problem with data, is we have to do many small operations over many elements, is to not do them in Python, to do them in NumPy or something like that, something else. And then like indexing is one of the core abstractions, and it's all about like building a mapping behind the scenes between labels that we care about and integer indexes that are sort of like an implementation detail. Blocks are like the abstraction through which we subset and change data. The underlying structure kind of helps you think about when copies are going to happen, because it makes it clear that when you're combining between different D types together, that's when you're going to end up with copies, or when you're doing fancy indexing. But just as like an aside, copies happen a lot. If you're using pandas, you kind of have to just be prepared that that's the case, and there are definitely a lot of like cool alternatives that handle that particular situation better. And then finally, just kind of that factorization is this interesting algorithm that's going on behind the scenes in pandas and powers the sort of like fast group by operations that you have. So guys, thank you very much. If I'm gonna like take questions now, but I am always interested. If you have like any questions that you don't want to ask here, hit me up on Twitter, GitHub. I'm essentially Jay Tratner on all forms of social media, including Instagram now. So there you go. Or you can send me an email. Yeah. So thanks. So any questions?
So about setting with copy.
Yes.
So, I mean, just like curiously, so if you were to treat your DataFrame as basically columnar and do like single column operations and then combine those at the end, are you going to pay the same copy cost, or like let's say you were to slice across multiple columns? Is that a reasonable way to think about that? Or?
Yeah, I mean, if you're getting like one column, then generally that's just like subsetting. I think the big idea with setting with copy is that it is more about just like, if you express the setting in one expression, then you can do the set in place as opposed to having to make a copy first or accidentally doing your operation on a copy. But yes, that's true. If you operated column-wise, that would also do the subsetting kind of view stuff.
Those data blocks are not blocked by rows at all, right? They're only columns at a time.
Actually, so yeah, they're blocked by columns, but at some level, like the distinction between rows and columns doesn't mean anything in pandas in particular, except for the fact that like pandas is column oriented in terms of its storage. But like, for example, if you wanted to iterate by rows in NumPy, you can actually do that. Like actually NumPy has the ability to change how its stride is oriented, which then changes the orientation. So pandas doesn't necessarily support that, but like under the hood or working with the values from a block, you can do that.
Did I understand you correctly that concat is less expensive than append?
Absolutely. So if you said, hey, I have like, I need to add, like, I have 5 chunks of 100 items, right? And you start with like one big data frame. If you did 500 appends or even 5 appends, then you're going to have 5 copies. Whereas if you concat all of those objects at once, then you don't end up with as many copies going on underneath the hood, because it's sort of only consolidating it into blocks once, I think. Any other questions? And feel free to correct me if you know better, because I, yeah.
What happens if the table is so large it doesn't fit in?
It doesn't fit into memory. If the table is so large that it doesn't fit into memory, there are a bunch of solutions that you can go to deal with that. And I think there are really good resources online that talk about options, right? Because essentially your options are to do some kind of like splitting your data into parts, processing each part individually, and then merging it back together. One of the biggest ways you can do that is using PyTables and HDF, because that can do kind of querying. But I mean, part of that is just like, if your data is really that big, Pandas is absolutely like a medium data solution. It must fit in memory and can't even take up all of your memory to do it. But obviously you can like split up the job. Oh, go ahead.
For loading data frames, is there a suggested way to declare the type of values and columns with Python so that when loading the entire data frame, that process is faster?
You can like specify types in the read CSV thing, I guess. So essentially, like if you're reading in data, you can say to it like, I'm pretty sure this column is going to be this column is going to be something else, so you avoid like the overhead of convert objects. I think beyond that, it's probably something more where like you construct it as an ND array first, and then pass it into the data frame constructor.
Is there a standard way to involve Python in that, or it wouldn't be advisable?
I think that's a really good question, if there's a standard way to involve Python in it, and I don't really have an answer offhand. So I think that could be a cool question to like send out to the PyData mailing list, which is like, I think it's like Pandas. Anyways, if you go to the Pandas website, there's a couple places where you can ask questions, and I think that would be like an excellent question with like a test case and stuff. So, cool. Well, guys, I think we got, relatively perfect time-wise, like the 40 minutes that I'm supposed to have for this with Q&A. So thank you guys very much for coming. I really appreciate it.